Hi students, in this video we are going to learn about the complete discussion about the various groups. We already know in the long form periodic table around 18 groups are there. We are going to discuss details in first group, second group, 13, 14, 15, 16, 17, 18 groups in an individual manner with their general representations. Before going to learn about the groups in a clear manner, let us discuss the basic concept of atom. You already know, in an atom, the center where the protons and neutrons are there, that is called nucleus. Electrons revolve around the nucleus in a definite circular paths. Those definite circular paths are called shells. The fixed path chosen by the electron to revolve around the nucleus is called orbit or shell. They are represented by letter n. N is equal to 1, that is k. N is equal to 2l. N is equal to 3m. N is equal to 4 n. This we already know. How many shells are there? Infinity shells are there. This is the fundamental basic we already given before. Now, if you observe, if the fourth shell is the outermost shell, not only fourth shell, fifth shell or sixth shell, final shell of the atom. This means the outermost shell of an atom is called valency shell. The outermost shell of an atom is called valency shell. Now, if the valency shell is n shell and the before shell, this becomes n minus 1. The shell which present before the valency shell. The shell which present before the valency shell is called penultimate shell. The shell before the valency shell is called penultimate shell. Good. If you come here before, here one more shell is there. This shell present 2 steps ahead. This means the shell present before the penultimate shell, which is nothing but n minus 2, we may write as the shell which present before the penultimate shell is called anti-penultimate shell. Depending upon this discussion, we are going to discuss about the groups in a very clear manner. Now see, come to the group 1. We are going to discuss the brief representation of the group 1. Group 1 elements are called alkali metals. Alkali metals. They are lithium, Li, sodium, natrium, Na, potassium, kalium, K, rubidium, Rb, cesium, Cs, francium, Fr. Lithium, sodium, potassium, rubidium, cesium, francium. From top to bottom is called as a group. Their atomic numbers are successively lithium atomic number 3, sodium atomic number 11, potassium atomic number 19, rubidium atomic number 37, cesium atomic number 55, francium atomic number 87. Now, if we are going on writing the electronic configuration, the atomic number is 3, the electronic configuration is 1s2, 2s1. With the atomic number 11, the electronic configuration is 1s2, 2s2, 2p6, 3s1. Atomic number 19, 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. Atomic number 37, that is for rubidium, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s1. If you are going writing for cesium with atomic number 55, finally we can get 6s1, and for francium we can get for 7s1. If you observe here, 2s1 is the outermost shell. Here, principal quantum number 3 is the outermost shell, means final electron enter into the 3s orbital. Here the final electron enter into the 4s orbital. Here the final electron enter into the 5s orbital. Next, the electron of cesium enter into 6s orbital and as well as 7s orbital. See here, the final electron of the electronic configuration is called differentiating electron. Final electron of the electronic configuration is called differentiating electron. Outermost shell also called valency shell. So here the valency shell is 2, here the valency shell is 3, here the valency shell is 4, here the valency shell is 5, here the valency shell is 6 and it is 7. If you observe that they are in the form of positive integers, we already know the positive integer is represented by letter n, and here it is s1, 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 s1. So we can write the general representation as ns1. What we already said, the differentiating electron enter into the s orbital. So these are all the group elements. All these group elements belongs to s block. These all the first group elements, their physical properties under metals means they are ready to lose the electron and they become an electropositive elements. For that sake only we can consider this as metals. Now the general electronic configuration or the general electronic EC, nothing but electronic configuration is NS1 for the group 1 elements. So the general representation is NS1. They are all S block elements and these are all metals. Let us discuss about the next group elements, that is alkali metals. Let us come to the group 2. Group 2 elements are also called alkali earth metals. Alkali means they can form bases. Whenever these metals react with oxygen to form their oxides, the corresponding oxides react with water to form bases. For that sake only we are calling as alkali. And these are all the metals are directly extracted from the earth's crust. For that sake only that is called alkali earth metals. Why it is metal? Because they are sonorous, lustrous, ductile and malleable, good conductors of electricity also. Now let us discuss what that group. The group 2 elements are beryllium, magnesium, calcium, strontium, barium, radium. Beryllium Be with atomic number 4, magnesium Mg with atomic number 12, calcium Ca atomic number 20, strontium Sr with atomic number 38, barium Ba with atomic number 56, radium Ra with atomic number 88. Now, if you write the electronic configuration of beryllium 1s2, 2s2, magnesium 1s2, 2s2, 2p6, 3s2, calcium atomic number 20, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, strontium 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2. Now if you observe here, valency shell is equals to 2. Valency electrons are also 2. Outermost shell of the electronic configuration is called valency shell. The electrons that are present in the valency shell is called valency electrons. Now observe here, valency shell is equals to 3. Valency electrons are 2. Now if you observe in the case of calcium, valency shell is equals to 4. but the valency electrons are 2 only. Outermost shell is called valency shell. So valency shell is 4. Valency electrons are 2. Even in the case of strontium also, valency shell is equals to 5. Valency electrons are 2. Once again, the outermost shell is here S, 5th shell. So valency shell is 5. And the number of electrons that present in the valency shell is called valency electrons. So the valency electrons are 2. Here valency shell is 6 and valency electrons are 2. Valency shell is 7, valency electrons are 2. And if you observe, the final electron of the electronic configuration that we are calling as a differentiating electron enter into the s orbital. So these are all s block elements. The general electronic configuration is ns2. Why? Because valency shell, valency orbital is s and 2 electrons are there. So their general representation is ns2. If the valency electrons are 2, they are ready to lose their electrons, and so they are called metals. Now let us summarize. For alkali earth metals, the general representation is ns2. Valency electrons are 2. In the name only there are metals. So all the metals are electropositive. Now let us discuss group 13 elements in detail. Group 13 is also called boron family. Why? Because they started from boron. The elements are boron, aluminum, gallium, indium, thallium. Boron, symbol B, aluminum, Al, gallium, Ga, indium, iron, thallium, Ti. Boron atomic number 5, gallium with 13, aluminum with 13, gallium 31, indium 49, thallium 81. Now if we are going on writing the electronic configuration of boron, 1s2, 2s2, 2p1. Now observe here, valency shell is 2, valency shell is 2, valency electrons are 3, here 2 and 1. Why? Because the total number of electrons present in the valency shell is called valency electrons. See, valency shell is 2 and the valency electrons are 3. Now comes to the aluminum, valency shell is equals to 3. Why? Because here and as well as here, and the valency electrons are also 3. Here 2 and 1. Out of 3 valency electrons, 2 electrons belongs to the s orbital and 1 electron belongs to the p orbital. That means differentiating electron, that is nothing but final electron of the electronic configuration is called a differentiating electron, enter into the p orbital. Even in the case of boron also it is enter into the p orbital. Now let us come to the gallium. Here we can arrange this, we can rearrange as 4s2, 4p1. By the rearrangement we can write the valency shell is equals to 4, valency electrons are 3. Now if by rearranging here also 5s2, 5p1, valency shell is 5, valency electrons are 3. By rearranging here of thallium with the atomic number 81, it can be written as 6s2, 6p1, valency shell is 6, valency electrons are 3. Now from this general explanation we can understand that the general electronic configuration becomes ns2, np1, where n may be 2. If n is 2, it can be 2s2, 2p1. If n is 3, it becomes 3s2 3p1. If n is 4, it becomes 4s2 4p1. If the n is 5, it becomes 5s2 5p1. If n is 6, it becomes 6s2 6p1. And their valency electrons are always 3. The final electrons, the total number of electrons present in the valency shell is 3. Now see, the differentiating electron enter into the p orbital. So these are all the elements, that is group 13 elements belongs to p block. Before only we said, if the differentiating electron enter into the s orbital is called s block element. If the differentiating electron enter into the p orbital is called p block element. If the differentiating electron enter into the d orbital is called d block element. If the differentiating electron enter into the f orbital is called f block element. See here, differentiating electron enter into the p orbital. So group 13 elements comes under p block elements. Group 14, which is also called carbon family, because they start from carbon. The elements are carbon, silicon, germanium, tin, lead, flerovium. Carbon, silicon, germanium, tin, lead, flerovium. Those symbols are: carbon stands for C, silicon Si, germanium Ge, tin, its Latin name is stannum, so its symbol is Sn. Lead, its Latin name is plumbum, so it is represented as Pb. Flerovium Fl. Right. Now come to their atomic numbers: carbon 6, silicon 14, germanium 32, tin 50, lead 82, flerovium 81. If you are going on writing the electronic configuration, carbon 1s2, 2s2, 2p6 comes here. Valency shell is equals to 2, valency electrons are 4. Now come to the silicon with the atomic number 14, 1s2, 2s2, 2p6, 3s2, 3p2. So here the valency shell is equals to 3 and the valency electrons are 4. Now if you observe germanium, by rearrangement we can write 4s2, 4p2. So valency electrons are 4. Here the valency electrons are 4. Valency shell is 4. Now whenever, if you move towards tin with the atomic number 50, by rearranging we can write 5s2, 5p2. Valency shell is 5 and the valency electrons are 4. So the general representation will be ns2, np2, where n starts from 2, 3, 4, 5, 6, 7. Now valency electrons are 4, where the valency electrons are 4, and at the same time the differentiating electron enter into the p orbital. So these are all p block elements. If the valency electrons are 4, these are all called as metalloids. Generally they are called as metalloids. Now come to the group 14. Their general representation is ns2, np2. Valency electrons are 4. They are metalloids. Generally they are all metalloids. Group 1 metals, group 2 metals, group 13 metals, whereas well as group 14 metalloids. Now the general properties of these group elements are always similar. Why? Because general electronic configurations are similar. Where the electronic configurations are similar, their properties are also similar. For that sake only, Moseley said, physical and chemical properties of the elements are the periodic functions of their atomic number or electronic configurations. Means total periodic table is depending upon the electronic configurations. Thank you.